Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to find the eigenvectors of a larger matrix. The process really is the same as what we've done before, but when you have larger dimensionality, it takes a little bit longer sometimes, so we'll get a lot of practice here doing it with a 3x3 matrix. The matrix that we're going to use is something we've seen before. We've already found the eigenvectors for it. 5, 4, 4, -7, -3, -1, 7, 4, 2. All right, that's the matrix. Now we've already found these eigenvalues in separate problem before. The eigenvalues is 5, 1, and -2. 5, 1, and -2. So we're going to get some eigenvectors associated with this, and with this, and they will together form what you call an eigenbasis for the eigenspace. I know that's a lot of eigens, but that's kind of the way you have to roll. So for the first eigenvector that we have, we're basically going to plug it into the characteristic problem, which is a minus lambda I is equal to 0, like this. And basically all you do is you take your A matrix and you plug in the eigenvalue into it. So it's going to be I minus the eigenvalue that we're doing is 5. Then we have 4, 4, -7, -3 minus 5, because we have to do it here too, and then -1, and then 7, 4, 2 minus 5. So all along the diagonal you subtract your eigenvalue, and then over here you'll have your eigenvector, and then you're setting the whole darn thing equal to 0. So you want to formulate this in terms of a matrix representation of the system of equations. 5 minus 5 is 0, and then 4, 4, and then -7, this is going to give you -8. -1, and then 7, 4, -3, and then since it's homogeneous, you just put zeros on the right-hand side. So really all we're trying to do is we're trying to find the eigenvector, the values of the vector that make this true. So what you would do is row reduction. You'd want to put ones along the diagonal as much as you could, zeros underneath it, and then you can kind of read the solution off, and we've done this many, many times with row reduction. I can do all those row reduction steps, but we've done them a lot of times, and I think for this type of problem, it's more illustrative if I just go ahead and show you what the row reduction looks like, because I don't want to get bogged down too much in the details because we've already done row reduction a lot. After you row reduce this, you will get something like 1, 0, -1, and you'll get 0, 1, 1. And you get 0, 0, 0, 0 here. So this is the row reduction form of this. Again, you do this going from here to here is several steps. We've done row reduction a lot. This is what you would end up with. Notice you do have zeros on one row, which implies you're going to have an infinite set of eigenvectors associated with this eigenvalue, which is very, very common. So what I want to do next is, I think to make it a little bit more palatable, I'm going to go over here and continue our discussion over here. Because this guy is all zeros, what it means is this equation you can think of as telling you something about x sub 1, this tells you something about x sub 2, this tells you something about x sub 3. Because it's all zeros, basically we know that x sub 3 can be anything. Because if you put a value for x sub 3 of anything in here, it can satisfy an equation with all zeros. All right? Then we move up to the next equation above it. I'll circle this because this will be important. The next equation above it is x sub 2 plus x sub 3 from here is equal to 0, but I already know what x sub 3 is. X sub 2 plus k is equal to 0, so x sub 2 is -k. So I'll circle that. And then we'll just continue on down and look at the first problem, or the first line here. This will be x sub 1, and then minus x sub 3 is 0. And x sub 3, again, I know what that is already. So x1 minus k is equal to 0. So x1 is k, like this. So what you're trying to do is you're trying to find what each value of x is in terms of the constant k, so that you can then write it down. You'll say that x is equal to x sub 1 is k, x sub 2 is -k, and x sub 3 is +k. Or you can just pull the k out, and you could say 1, -1, 1. 1, -1, 1. So the eigenvector associated with this eigenvalue of lambda is equal to -5 is this guy. So this is the eigenvector. And notice that it's an infinite set of vectors. Basically, it's any multiple of this vector here is an eigenvector associated with this eigenvalue. All right, now I'll write it all down and summarize it when we get to the end of the problem in a minute, but let's for now go on to the next eigenvalue. What if lambda is equal to 1? Well, I go back to my original matrix, 5 minus 1, 4, 4, negative 7, negative 3 minus 1, negative 1, 7, 4, 2 minus 1, and basically I'm going to set this and put zeros here because I'm trying to solve this little system of equations to figure out what my vector is that makes this true. Okay, so then what I'm going to have is this will be 4, 4, 4, negative 7, negative 4, negative 1, 7, 4, 1, 0. Right? Just like that. All right, and then I'm going to do row reduction. And again, I can do this myself, but I'm basically going to try to get zeros here, and I'm going to try to put ones on the diagonal and try to get zeros above, and basically I'm going to try to solve it all. Whenever you do that, you're going to end up getting about this far before you can go any farther. 1, 0, negative 1, and we've done row reduction so much that this shouldn't come as a surprise to you. 0, 1, 2, 0, 0, 0, 0, 0. Again, I have all zeros, which leads me to believe I'm going to have an infinite set of eigenvectors associated with this particular eigenvalue. And so I'm going to take this and I'm going to continue the discussion over here. The third row is 0, so again I say that x sub 3, the third variable, is equal to anything I want it to be. And I'll circle that because that'll be important. The next equation above it is x sub 2 plus 2x3. x2 plus 2x3 is equal to 0. x2 plus 2 times this, I know that it's equal to k now, and then x2 is equal to negative 2k. x2 is equal to negative 2k, and I can circle that, because that'll be important in a minute. And then finally, the top equation is x sub 1 minus x sub 3 is equal to 0. So x1 minus x sub 3 is k, is 0, so x1 is k. And I can circle that. And then finally, to write it all down, the eigenvector here, x, is going to be x1, x2, x3. x1 is equal to k, x2 is negative 2k, and x3 is equal to k. Or you can write it as, you can pull out a value of k, and then you'll have 1, negative 2, and 1. 1, negative 2, and 1. This is the eigenvector associated with lambda is equal to 1. I'll summarize everything in a final conclusion in a minute. But we have more work to do because the other eigenvalue, there's 3 eigenvalues to this problem. That makes it a little bit long. The last eigenvalue is negative 2, so we have to do the same process again. So we go back to our matrix and say 5 minus negative 2, 4, 4, negative 7, negative 3 minus 2, negative 1, 7, 4, negative 2 minus a negative 2. Actually, this is not 3 minus 2. This is 3 minus a negative 2 because we subtract the eigenvalue. And then this is going to be, well, you know what, we'll just make it an augmented matrix right now. Since we know we're going to set it equal to 0, we'll just put the zeros in here like that. So we basically have taken the eigenvalue, we put it back into the problem, and what we end up getting, 5 minus negative 2 is 7, and then we'll have 4, 4, 0. This is negative 7. This becomes negative 3 minus a negative 2 is going to give us negative 1, and then this is negative 1, 7, 4. Now I made one small mistake. This is not a negative 2 here. That's a positive 2. If we go back to our original matrix, we had a positive 2 there. I just kind of got a little bit carried away here. So it should be 2 minus a negative 2, which should give you a 4 down here. Let me double check this matrix is correct. 7, 4, 4, negative 7, negative 1, negative 1, 7, 4, 4. That's right. All right, so then we try to solve this. So we do row reduction. And what you will get when you get down to business on that is 1, 0, 0, 0, 1, 1, and 0, 0, 0. Again, you see you have this constant pattern of getting all zeros when you try to do this. That tells you you're going to get an infinite set of eigenvectors. So the third row tells us that x sub 3 can be anything we want. So I'll circle that. The next row above it is x sub 2 plus x sub 3. X sub 2 plus x sub 3 is 0. So x sub 2 plus, we know this is now k. So x sub 2 is negative k. We'll circle that. That's going to be useful. And then we will say the top equation, 1, there's nothing else there. So it's going to be x sub 1 is equal to 0. What we find from here is that x sub 1 is equal to 0. There's no k or anything like that involved in it. You just read it straight out of the row reduction. X sub 1 is actually equal to 0. All right, so what we're going to have here, the eigenvector x is going to be equal to, for x sub 1 you get 0. For x sub 2 you get negative k. For x sub 3 you get positive k. And you can, of course, factor out a k. This is still going to be a 0 up here. This will be a negative 1. This will be a positive 1. So this will be the eigenvector associated with the eigenvalue, negative 2. All right, so I agree. It's a long, tedious process. That's why I wanted to go through the whole thing with you. So let's go ahead and summarize our results on the following page. Okay? Let's summarize our results on the following page. What we know now is that when lambda is equal to 5, that's one of the eigenvalues, then the eigenvector x is equal to k, 1, negative 1, 1. That's the eigenvector, okay? Then we also know that when the eigenvalue is equal to 1, then the eigenvector associated with that is 1, negative 2, 1. K. That means an infinite combination of those. And then finally, the last eigenvector we had, or eigenvalue we had, was negative 2. And the eigenvector associated with that is 0, negative 1, 1. That's what we just found. So for each eigenvalue we have, basically we have an infinite set of eigenvectors because k can be anything. It's any multiple of these vectors can go along with that. But the base vector in each of these cases, we give a special name. So we say the basis vectors for the eigen space, or you can also call it eigenbasis, sometimes you see that, is 1, negative 1, 1, 1, negative 2, 1, 0, negative 1, 1. There's lots of eigens here. Basically, the bottom line is you're going to end up finding these base vectors, these basis vectors, and you can list them as your kind of fundamental eigenvectors, but really for every one of these eigenvalues, there's an infinite set of eigenvectors, as you can see by the multiplicity with the k here. All right, so that pretty much does it. We have learned what eigenvalues are and the characteristic polynomial to find them. We have learned what eigenvectors are, and we've listed them here. Now these vectors, because these are eigenvectors, are by definition linearly independent. If you put this into the test for linear independence, you will find that these are linearly independent. So none of these vectors can be written as a combination of the other two. That means they're unique, they're different, they're not, they're not written as a combination, they're not like a hidden little combination of the other guys. They truly are independent, pointing in different directions, etc. So that covers eigenvectors, eigenvalues, and that covers this set of lessons here. We've covered a tremendous amount of material from transformation matrices on into rank of a matrix, and we've covered determinants in great detail, and we've covered linear independence and eigenvalues and eigenvectors. It's a lot of material, but all of it is absolutely essential to anyone studying linear algebra, and all of these concepts are really going to be useful to topics outside of linear algebra, into differential equations, into engineering courses. You're going to be using them a lot. And so I hope that I've given you enough problems to give you a little bit of a better understanding than you had when you walked into it. And hopefully now you can open your textbook, whatever book you're using, and read the theorems and read what they're talking about. And having this as a background, you will be able to much more easily understand what they're saying. But when you open those books a lot of times and look at them, if you don't know what they're already trying to tell you, sometimes it's hard to understand what they're trying to say. So keep all of these ideas in your head. Go off into your book, solve extra problems. Good luck on your tests, on your quizzes, on your exams. I'm sure you'll do fine. Make sure you can do these problems, and I think you have a very good, well-rounded background in this part of a linear algebra sequence.